Hello, I hope you're doing well. I'm Hassam Kushiki and I will serve you uh, the clustering algorithm description for session season 9 of the book. Uh, First, let's see what the contents are available in this presentation. First, we will delve into clustering algorithms. We give you an introduction about them. Then we see the evaluation measures. After that, we will see and go through the Cummings algorithm, and then we will see Birch-Biko and clustering algorithm. And then we see the density-based methods such as dbScan and dnstream, and after that we see clustering. Finally, we check the streamcom++ as well as their courses. Well, first let's get an introduction for clusterings. Clusterings are unsupervised learning machine learning algorithms because in clustering we don't have labels for our data. Uh, for clustering, we have three assumptions. The first one is that instances are points in some space that we can probably visualize them if they are in 2 or 3 dimensional. Um, After that, we have to have this assumption that we can impose a distance function called d to measure the distance between data points. And finally, we can uh, see that more similar instances are closer in this distance based on the function d that we have implemented in assumption number 2. There are different types of clustering. The first group is that we require as a user to specify a value for k. And the other type is that the algorithm itself determines a number for clusters by itself. If k is not bounded here, we may face a problem. Let's assume that assigning an instance to a cluster by itself leads to a clustering with the cost of 0. It means that each data points in our algorithm will assign to a specific cluster, and the number of clusters will be equal to the size of our dataset equal to number of p data points in our dataset. So we have to penalize this um, function and avoid that to assign each data point to a specific cluster. Uh, let's check out the evaluation measures. We have two evaluation types. The first one is structural or internal, and the other one is grant roof based. The first group has cohesion, SSQ, separation, and Stillhoughty coefficient, if I pronounce it correctly. And the other one is grant roof based, which has accuracy, recall precision, purity, and cluster mapping measure. The first one, let's define the options for that. Cohesion means the average distance from a point to its assigned cluster centroid. In this measure, the smaller the better. SSQ is the next one. It means the sum of the skewered distances from data points to their assigned centroid. And in this one, um, as well as the previous one, the smaller the better. Separation means that average distance from a point to the points assigned to the other clusters. And here the larger the better, because we want the better separation for this measure, and if it is bigger and larger, it means that we have better separation. The Stillhoughty coefficients means the ratio between cohesion and average distances from the point to their second closest centroid. Here we implement a good cohesion and a good separation combined. The next group is grant roof based, and the accuracy is defined as the fraction of the points assigned to their correct clusters. The recall is defined as the fraction of the points of a cluster that are in fact assigned to it. Precision means that the fraction of the points assigned to a cluster that truly belongs to it. And purity is defined as in a maximally pure clustering, all points to in the cluster belong to the same ground truth class or clusters. And here we may have labels for the datasets to check if we are clustering them in a correct way or not. The last one is cluster mapping measure or CMM, which means specifically designed to evolving data streams, meaning that streams are changing over the time, and this one considers merges and splits of the cluster over the time, but it may create some errors. Both of these techniques work well if the number of clusters is fixed and not changing over the time, and when clusters and their centroids evolve over the time, we may use EWMA or exponentially weighted moving average accumulator or a sliding window to take into account the latest changes or features. Now it's time to check the Cummings algorithm. The key point is that the Cummings is very simple, but the cost selection is very important, and this algorithm is highly depends on the initial random for checking the assignment state. And this algorithm is very sensitive to outliers, and it will struggle with high dimensional datasets with lots of features and dimensions. The Cummings clustering algorithm works by randomly choosing cost centroids for each cluster and then assign each data point to the nearest centroid. After that, it calculates the mean of all data points and moves the centroid to the mean of those data points. This procedure will be repeated until two circumstances. The first one is that no more moves is available and happening to the calculating the mean and moving them, or we reach a maximum number of iterations. Let's visually see how it works. First, at A, we have our data sets with no labels assigned. In B, we assign two random centroids. In C, we calculate the measure from all data points to their nearest centroids and assign that centroid to that class. In D, we calculate the mean and move the centroid to the mean. In E, we again calculate the um, distances, and in F, we again move the centroid to the mean, and here the algorithm probably won't move, and we stop calculating and moving a centroid. Cummings has several variants. The first one is Cummings++, which is a more stable method compared to the purely random initialization because it uses a new initialization step. It is faster in convergence, and it tries and always reaches to the better local minimum. The other variant is called StreamCon++. This is not very straightforward and used for streaming data, and it has one offline and online phases. The online phase summarize or actually make an sketch for clusters called microclusters, and it works on all the data. The offline phase uses those summaries to compute the final clustering efficiently. It can be applied and run on either regular time intervals or on demand whenever we need that to get updated. The next we reach at Birch, Biko, and clustering algorithms. The first one is Birch. BIRCH is a summary of balanced iterative reducing and clustering using hierarchies. It is incremental. We can add clusters to it, and it uses a clustering feature called CF vector to represent microclusters. A CF is defined as a tuple of n, ls, and ss. N is defined as number of data points in the CF. Ls is the d-dimensional sum of the n data points, and ss is the d-dimensional sum of squares of the n data points. CF is additive. It means that if we have CF1 plus CF2, it means that they are they can be added pair by pair with their corresponding features. Here, a distance from a point to a cluster is the average of intercluster distance, and the average of intra-cluster distances are very easy to compute. Um, the CF trees use a height balanced tree to uh, keep control of the height of the tree, and CF trees have two parameters. The first one is the branching factor of B, which means the maximum number of children that any given node may have, and the node here is defined as the cluster summary of data points. The leaf radius threshold of R is defined as all points represented by a leaf fall in a ball of radius. And here every leaf and also every inner node contains a CF vector that we have defined earlier. The BIRCH has four phases. The first one is to scan all the data and build an initial in-memory CF3. The second one, which is offline, is condense the CF3 into a smaller ones. This is optional, but is good for efficiency. The next phase is offline again, and it clusters them globally, batch the clusters based on the CF3, and the last one is refining the clusters, which is again optional and requires more iterations and passes. There is a flow for BIRCH phases. First, for the student data arrive, the tree will be descended and we reach the closest leaf. Here we check if that data can be absorbed in that leaf. If it can, uh, so we update the leaf statistics. If not, a new leaf will be created. And here, if we are in the parent node and the parent node has more than B child, we split it into two and we recursively go until we reach the root, or if not, a new leaf will be created. Here we try to merge leaves and nodes that may become too close in the process. The BICA algorithm will combine the data structures of BIRCH with the theoretical concepts of courses for clustering. The courses are explained in details in section 7. The goal of BICO is to find a reduced set that is not only small, but also offers guarantees of approximating the original points sets. The next algorithm is clustering. Clustering is an adaptive extension of BIRCH that can deal with changing streams. Recall the N, Ls, and Ss tuple. Here we have defined these N, Ls, and Ss. For clustering, we add two more features to the tuple called LT and ST. And LT is the sum of the timestamps, and ST is the sum of the skewers of the timestamps. Let's see how it works. The cluster name keeps the maximum number of microclusters in the memory. If a point arrives and requires the new microclusters and there is no more space available, it can delete the oldest microclusters or merge the two oldest microclusters. Here, the uh, oldest is defined as the significant uh, recent activity in the microcluster and not the time. That is because the snapshot of the clustering is can be defined in a desired time frame, and it gives more resolution to the more recent time frames and less resolution for the furthest data points in our time frame. We reached the density-based methods and they will be discussed and give you the presentation by Miss Nurizad.